most welcome on our study today. We are going to look at hydrogen as an element of chemistry, and when it comes to hydrogen, we are going to see to it that it forms hydrogen gas, and that is the format in which it normally exists. So definitely hydrogen is one of the smallest and the lightest gases we know on this planet among the first 20 elements we look at, and it usually does not occur in free state, but in combination with water, sometimes in acids, because we all know that an acid, when you dissolve it in water, it releases hydrogen ions as the only positive ions in solution. Then it can be part of hydrocarbons and some other organic compounds. So within those compounds, differently, we find hydrogen, and we can use it to handle different things. So hydrogen, we are going to look at how we can prepare it in the laboratory, and there are two methods of preparation of hydrogen. We can be requested to prepare a dry sample of hydrogen, or simply we can be requested to prepare hydrogen as hydrogen gas. So normally we use two substances to prepare hydrogen, like you're seeing there. We can use dilute hydrochloric acid, and sometimes we also use dilute sulfuric acid. We use the action of those two acids on different metals, but especially in the lab we use magnesium or zinc. Those are the two metals we tend to use to come up with how we can prepare a sample of hydrogen. This sample of hydrogen, like I've told you, we can be requested to prepare just hydrogen gas, just that. So the setup we are seeing here in the drawing is a setup that prepares hydrogen gas. But if they put a condition of preparation of dry hydrogen, then the setup will change. In this setup, we see that zinc granules are placed in a flat bottomed flask. For all reactions where we don't have heating involved, make sure that the flask you use is a flat bottomed flask. Then zinc granules are put in this flat bottomed flask because it is a solid, it can't flow. You're going to add dilute sulfuric acid to the zinc granules such that the reaction takes place. To prevent the gas from escaping, we ensure that the flat bottomed flask is cocked such that there is no escape route of the gas formed, apart from the delivery tube which we connect, that directs the gas through a water trough, and the gas will be collected over water in a gas jar. So the method demonstrated by this is a collection over water, because hydrogen is insoluble in water. So we tend to see that this method of preparation of hydrogen is not preparation for dry hydrogen. So if they don't specify, just be open and draw such a kind of setup of preparation of hydrogen. When we come to describe the setup we've seen here, we go ahead. Actually, the best thing is to describe how we prepare hydrogen, which is a dry sample. And if I'm to prepare a dry sample, like I've seen in the previous drawing, the zinc granules are going to be placed in a flat bottomed flask, which has a tap funnel, because the zinc granules are solids, they cannot flow. So we are going to connect the entire setup fully on a U-tube, which is going to contain our drying agent, and then we are to add dilute hydrochloric acid slowly to the zinc granules in the flask, and the dilute hydrochloric acid is going to be added by the tap funnel because it is a liquid, and therefore dilute hydrochloric acid can flow. Immediately, the two are mixed, zinc and dilute hydrochloric acid are mixed. We are going to see that hydrogen bubbles are going to be given off in form of a colorless gas. And these bubbles are going to be directed by a delivery tube into a U-tube containing anhydrous calcium chloride. Because this is a drying agent, it is hygroscopic with a high affinity for water, and therefore it is going to absorb the water vapor that has come along with hydrogen so that hydrogen can dry. The other reason as to why we are selecting this as a drying agent is because it cannot react with hydrogen. If you don't select anhydrous calcium chloride as a drying agent for hydrogen, you are free to use concentrated sulfuric acid as a drying agent because it does not react with hydrogen and also it is hygroscopic. After getting or drying your hydrogen very well, you're going to collect it by method of upward delivery because, like I started, hydrogen is one of the most light gases we know. So because it is less dense than air, we are going to collect it by a method of upward delivery. For every process you describe, make sure you put an equation. That's why I'm also writing an equation down there that zinc granules, which we've seen that they are solids, are going to react with hydrochloric acid to form a salt and hydrogen only. The reaction we are writing here comes from a reaction of an acid with a metal, that the products we form include a salt and hydrogen only. So that property gives us a method of preparation of hydrogen, and that is how we are preparing our hydrogen. The equation should balance. Since the valence of zinc is 2 and the valence of chlorine is 1, we tend to write the formula of zinc chloride like that. And hydrogen gas, hydrogen exists as a diatomic molecule. That's why we write H2 in gas. Because of these 2's, we were forced to balance the equation by putting a 2 on hydrochloric acid, such that we come up with a balanced equation of how to prepare hydrogen gas. So with what we've described here, we can come up with a drawing which can show to us how we can prepare dry hydrogen. And the drawing should involve a drying agent. So, like we've said, put dilute hydrochloric acid in a tap funnel, allow it to enter zinc granules such that the reaction occurs. The gas given off after the reaction is going to be directed into a U-tube by the delivery tube here. The U-tube contains anhydrous calcium chloride, which is responsible for drying our hydrogen, and then the dry hydrogen is going to be collected by upward delivery because it is less dense than air. So with the drawing, make sure that what you draw, you can use it to come up with a description like I've described above. That's simply how we can prepare a dry sample of hydrogen. However, the reaction might be slow, and there are ways through which we can increase the speed of this reaction. If you want to speed up the rate at which hydrogen is produced by the methods we've seen above, we can use or we can add copper 2 sulfate, anhydrous copper 2 sulfate. This one is a catalyst that will increase the rate at which the reaction occurs by lowering the activation energy. And catalysts, like we've defined there, are substances which will alter the rate of a chemical reaction, but the catalysts will not take part in that chemical reaction. That's why when we are writing the equation, we do not include copper 2 sulfate, because copper 2 sulfate is simply a catalyst. So This one can be inserted into the description if you want to insert it into the description we've used in preparation of hydrogen. Insert it at a point which says that actually when we added zinc into a flat bottomed flask, then add a little copper to sulfate to speed up the rate of the chemical reaction. You can insert that point there, or you can ignore, because this is simply a catalyst. Even if you don't put it there, the reaction will proceed. The second, if you want to increase the speed at which this reaction occurs, we can use zinc powder instead of the granules, such that we present a larger surface area for the reaction to take place. So those are two ways through which we can increase the rate of a reaction, or two ways through which we can increase the rate of hydrogen production. This takes us to how this gas can be identified in the lab. If we have very many gases which are colorless, but how do you detect that this particular gas, however much it is colorless, it is hydrogen? So we come on to the test for hydrogen, and when we are testing for hydrogen, we use a lighted splint, just like you see here. Sometimes we call it a burning splint. So when you hear burning splint or lighted splint, we are testing for hydrogen. So if you bring this burning splint near a jug or a boiling tube containing hydrogen gas, this hydrogen is going to explode with a pop sound and a blue flame. That's why I'm showing you here that if I bring the burning splint near a boiling tube of hydrogen, there is going to be a pop sound coming out, just like if you're flying popcorns. The sound that they give when they are bursting, that pop sound, is the one that hydrogen will also give when you bring a burning splint near a jar of hydrogen. So this test will have an equation. You're burning hydrogen itself, and the component of air that supports burning is oxygen. So in this test for hydrogen, we are going to see that hydrogen reacts with oxygen to form a liquid known as water. However, this water, because of the temperatures, it is going to be in form of steam, in form of vapor, but we don't mind if water is in liquid state or vapor state. It is free for you to represent water with a state of a liquid. If you feel like you want to put gas, because the water formed is in form of vapor, it is also free. We don't become strict on the state of water. So the hydrogen produced, all hydrogen gas, has very many properties, both chemical and physical. But among the physical properties, we look at cheap things here in terms of the color of the gas. So hydrogen has no color, it is colorless, just like oxygen, just like carbon dioxide, just like nitrogen, just like sulfur dioxide, just like very many gases we've thought about or we have learned about. Hydrogen is very light. That's why we even collect it by upward delivery when it is dry. This hydrogen is insoluble in water. That's why if we are not requested to prepare dry hydrogen, we can collect hydrogen over water. It has no smell. You cannot smell it and feel like, this is hydrogen. It is neutral. It is neither acidic nor alkaline. Even if you insert litmus paper, the litmus papers will not change in any way. This hydrogen will burn with a blue flame. That is under the test for hydrogen, that when you put a burning split near a jar of hydrogen, it burns with a blue flame and a pop sound. At least try to get that, such that you are in a position to look at how hydrogen is tested. Among the chemical properties, here we look at properties that involve equations and reactions taking place. And one of them is how hydrogen is going to react with oxygen gas. In this drawing, you're seeing that hydrogen gas bubbles are formed if zinc is added to sulfuric acid. The reaction will take place and hydrogen is produced. The hydrogen produced is directed into a water trough, and because hydrogen is insoluble in water, it's going to rise up as bubbles. So those bubbles, when you light or you hold a burning split near, as those bubbles rise up, the hydrogen will burn in oxygen with a blue flame and a pop sound to produce water. So there will be an explosion that will take place to form a colorless condensate. We are calling it a condensate because water vapor will condense as it reaches the cooler temperatures away from the burning splint. So colorless condensate is formed, and this condensate is for water. So hydrogen burns in water to form, burns in oxygen to form water. The equation should balance. That's why I've emphasized that any equation you write must balance. Hydrogen is 2 plus O2 oxygen, we form H2O. So to balance for the oxygen, we multiply the water by 2 and it makes hydrogen to be 4. That's why we are also multiplying the hydrogen by 2 to make them become 4. So with preparation, with the first reaction of hydrogen with oxygen, it gives us even the test for hydrogen. So we are seeing a colorless condensate, and this condensate is water. We come up with how we can test, or we can discuss something concerning that. Reaction of hydrogen with metal oxides. In this reaction, hydrogen behaves as a reducing agent, and there are oxides which are going to be reduced by hydrogen. Among them, these hydrogens, these oxides that can be reduced by hydrogen include the following. Among them, we have copper 2 oxide, which can be reduced. We have lead 2 oxide, it can also be reduced. And we also have iron 3 oxide, which can also be reduced. However, oxides of iron are all reduced by hydrogen. Sometimes they're going to give you iron 2 oxide or tri-iron tetraoxide. All those oxides can be reduced by hydrogen as long as the oxide is for iron. So in reaction of hydrogen gas with metal oxides, this hydrogen gas behaves as a reducing agent. It's going to remove oxygen from the oxides, and the products are going to be a metal and water. So we try to define what simply reduction means, and reduction is the removal of oxygen from a metal oxide by hydrogen, and sometimes it can be addition of hydrogen to an element or an atom or a compound, depending on how. It has 3 definitions, but today we are emphasizing removal of oxygen from a metal oxide. If it reacts with copper 2 oxide, we are going to form copper and water. If it reacts with lead 2 oxide, we are going to form lead and water, just like these equations tell us. And if it reacts with iron 3 oxide, we are going to form iron and water. So either way, we have to get a metal free of oxygen and water. So the task is going to be to state what was observed. I would like to affirm to you that copper 2 oxide appears to be black, and copper as a metal is normally used, copper solid is normally used as copper powder to form copper gall, and that copper gall is always brown. So copper in solid state, copper alone is brown. and water in this case is going to be given off in form of steam. So you're going to see a colorless condensate. So if I'm to write an observation for this equation in particular, I will say black solid for copper oxide turned to a brown solid and a colorless condensate formed. If I'm to write an observation for the second equation here, lead oxide, the condition here is heat. Lead oxide is reddish brown when hot. However, lead metal is brown. Lead metal is gray, and water is a colorless condensate because it's going to be given off in form of water vapor. So if I'm to write an observation for this one, like I also request you to write the observations, I'm going to say reddish brown solid turned to gray and a colorless condensate formed. Lastly, if I'm to write an observation for this, I'll also say reddish brown solid, because iron 3 oxide is brown. Reddish brown solid turned gray and colorless condensate formed. So that's how hydrogen reacts with metal oxides. Make sure that for any equation you write, you can also write an observation, and you can go as far as identifying which type of reaction is taking place. When you look at critically these equations, hydrogen removes oxygen from copper, such that copper becomes copper alone in metal form. And the oxygen from copper is taken up by hydrogen. So one compound is being reduced as the other is being oxidized. So collectively we call such a kind of reaction a redox reaction. I tried to represent that reaction in a diagram, that if I have hydrogen entering, substance A must be a drying agent. Name any drying agent that can be used to dry hydrogen. This hydrogen will be directed into a combustion tube or an ignition tube, where we have copper to oxide that is heated. So the conditions for hydrogen to react with copper to oxide are two. Number one, copper to oxide must be heated. And the second condition, hydrogen must be dry. Okay? So copper to oxide will be reduced by hydrogen to form copper and water. In this equation, copper to oxide is being reduced to copper, and in so doing, hydrogen becomes the reducing agent. However, in the same reaction, the hydrogen is being oxidated to water. So in so doing, in this equation, copper to oxide becomes the oxidizing agent because it has oxidized the hydrogen from hydrogen to water. So collectively, the entire reaction is going to be called a redox reaction. Why? Because it involves both oxidation and reduction. As we proceed, like I've told you, in this property, hydrogen is behaving as a reducing agent, and reduction is addition of hydrogen to a substance. It can be removal of hydrogen from a substance. It can be removal of oxygen from a substance, regarding what we have discussed. Reaction with chlorine, the mixture will explode in presence of sunlight to form misty fumes of hydrogen chloride, and that equation represents the reaction. Reaction with reactive metals like sodium It will react to form hydrides, like sodium reacts with hydrogen to form sodium hydride. As we proceed, we look at the uses of hydrogen. Where is it applied in our daily life? Number one, it is used in filling air balloons because it is light. You've seen these balloons are also being used as means of transport in hilly areas. So if you want to use them, if you want to see them being used, you can even go to Rwenzori side of Uganda. They are being used and they are very common in movies still. Two, hydrogen is used in hardening of oil in a process known as hydrogenation. If we go to margarine forming companies, companies which make blue band, companies which form margarine for cakes, companies like Bidiko, and Mukwano, you're going to find these things there. As we proceed, it is used in manufacture of petrol and coal. Students who come from Hoima region now are going to be experiencing this because at least we have petrol that side. Then it is used in manufacture of ammonia on a large scale, and that large scale process we call it the Haber process. Still it is used in oxyhydrogen flames for cutting metals and welding of steel. I think this is very common. If you've seen these welders, the flame that comes from those gas cylinders is always kind of blue or purple. So they use that flame. Hydrogen is part of it. Then manufacture of hydrochloric acid, because in almost all acids, hydrogen is part of it. So those are some of the things hydrogen will do. So we summarize hydrogen gas by leaving a few questions that I would love you to attend to. And if you find any challenge, please feel free. Talk to us, WhatsApp me. I will at least guide you in that aspect. A dry sample of hydrogen can be prepared in the lab using zinc and dilute hydrochloric acid in presence of a catalyst. You are requested to draw a diagram to show how we can prepare a dry sample of hydrogen. You are requested to identify that catalyst. Which catalyst do we use in preparation of hydrogen? Write an equation leading to formation of hydrogen gas and state how hydrogen gas can be identified. Then dry hydrogen was passed over heated lead-2 oxide. I've been mentioning the observations here, so if you listen to my video carefully, you're going to find these things there. State what was observed, write equation for the reaction that took place, among others. 2011, you're going to find a question in the 2B, write equation for the reaction between magnesium ribbon and dilute sulfuric acid. How can the reaction be made faster? That is how preparation of hydrogen can be increased. Name one metal that would react with sulfuric acid in a similar way like magnesium. If I don't use magnesium, which other metal can I use to prepare hydrogen? State what, explain why hydrogen cannot be prepared from dilute sulfuric acid and calcium or lead. These two metals can't be used if at all you're using sulfuric acid. One, because calcium will react with dilute sulfuric acid if you use those two to form a sparingly soluble calcium sulfate, which stops further reaction. And we are representing calcium sulfate with a solid state because it hardly dissolves. So we cannot use calcium and sulfuric acid to prepare hydrogen in the lab. Two, we cannot use lead because lead will also react with dilute sulfuric acid. However, the reaction produces lead to sulfate, which is completely insoluble in water, and it's going to be observed as a white precipitate. And this one will coat on lead, preventing further reaction, represented by the equation shown below. And today that's all.